Alright, so today's lesson is going to be on related rates. Okay, so first thing I want to say about related rates is that they're usually something that encompasses some sort of physical situation, so it's something you're going to try and imagine. So always draw a diagram if possible. Always. Help you envision the process. So let's go over a little example here. So one example is, let's say that we have a cube and it has a side of length x. So we have some cube. This drawing is not going to be exactly perfect. It's going to be some length x. And we have some volume in here, v. And we want to find the rate at which this volume is changing, or the related rates of this volume. So one thing that we know is that, well, what is the formula for the volume? The volume is simply length times width times height. In this case, we have x times x times x cubed. Pretty simple. Okay, so if we want to be able to find the rates that's going on here, so obviously a rate is something that happens with process of time usually, especially in a physical process, because everything we have, is governed by time. So if we want to find the derivative of v with respect to time, it's as simple as just taking the derivative with respect to time of xt. What that gives us is 3x squared times dx t. And as simple as that. That's our related rate. And the idea is here is that you're finding the change in the volume with respect to time in terms of the dimensions with respect to time. Okay, so let's go on to a little bit more of a complicated example. And this is one of my favorite ones to do for this, since I like to call it the ladder example. So the question is, a ladder sliding down a wall at a rate of, or speed of, 0.15 meters per second. Okay, so that's what's sliding down the wall. So we draw a little diagram here. We have a wall and a floor. We're going to have some ladder that's leaning up against the wall. So we know that it's moving down this way, 1.5 meters per second. Okay, we don't know what that height is yet. We don't know what that point is yet. We have no idea what rate it's going to be moving up this way yet. Okay, so when the ladder reaches a point at 3 meters, sorry, the bottom of the ladder, to be more specific, so, and we know it's coming away from the wall at 0.2 meters, this is given to us. We want to know, what is the length or the height of this ladder? So, using the situation we have going on here, we need to use these few things we know, these three things, to find the height of that ladder. So, that's going to be a right angle triangle. And since we're dealing with rates here, we're going to try and use the rates to find out what the positions are here. So the best way to do this is that if you look at a triangle, just like anything, you have a squared plus b squared equal to c squared. Pretty simple. So we have our x squared plus our y squared. It's going to be equal to the height of the ladder squared. Now, what's going to happen is that we want to take the derivative of both sides of this, just like we did last time. It's just like the related rates. And what we're going to do is that we need to find the rate, or using the rate that we have, we need to find the point right here that that ladder is going to be at when the ladder is at that point 3 meters. If we can find that point, we can use those 2 points back in with our equation here, Pythagoras theorem, pretty simple, to find out what this height h is. So what we're going to do is taking the derivatives of both sides, and we're going to do that with respect to time. And the reason we know to do that with respect to time is because it tells us right here when the rates that are given. It's meters per second. tells us we're dealing with time here. So we only have, in our whole situations going on here, we only have space components. We have x's and y's. We don't have anything with time. So in order to get a rate with time, we need to differentiate this equation with respect to time. Alright, so in doing so, simple derivatives. Alright, so we know from any time before, we're going to have our power rule. It's going to give us 2x, and then you're going to have, from the chain rule, dx dt plus 2y dy dt. And since our height is a constant, we're going to have 2h dh dt, but that's going to go to 0. So the whole thing is going to be equal to 0. So what we need to do is that we need to solve for where the ladder is going to be at our y location when the bottom of the ladder is located at x is equal to 3. So plugging everything into what we have and solving, you remember what we have now is 2x dx dt plus 2y dy dt equals 0. So what we're going to obviously do is we're going to try and isolate that y component and solve for that. Those are going to cancel. I'm going to bring a y over to the other side. Oh, sorry, I'm a little ahead of myself there. We're bringing our dy dt over to the other side, and we're solving for our y. And what's going to happen, that's going to leave us with y is equal to negative x dx dt over dy dt. Plugging everything in, this was 3 meters, and I believe that our change of x was 0.2 meters per second. Yes, it was. And that was all divided by negative, because we're moving down the wall 0.15 meters per second. So, doing the quick math on that, that's going to leave us with y is equal to 4 meters. Plugging that back in to our y equals mx plus b, or sorry, not y equals minus b, a squared plus b squared equals c squared, or Pythagoras theorem. Simply going to solve for the height, h, and in order to do so, we now have this right here, which is pretty simple to solve for. And that's just going to leave you with h is equal to 5 meters. And that's a pretty simple related relates question.